Hello. Welcome back. So, some announcements. Given where I think many of us are at, and how much has been going on in the last week or so, what I decided we're going to add one more problem to the assignment, that it would all be due next week. Okay, so we'll have more time to work on it and think about things and digest things. Right, and we will have a makeup lecture, but we'll do that in April sometime. After spring break. All right. All right, let's sort of try to get back and think about where we were, what we were thinking about. Get back to gear on the subject matter. So we're talking about squeeze states. Okay, what we talked about in the last week previously is about the algebraic properties of the squeeze states and how in principle we would detect squeezing. Okay, so as we've discussed now many times, but I'll remind you again, the kind of star of our show is this thing we call the squeezing operator. And it has, for a single mode of the electromagnetic field, it has this form. Okay, now you're studying in your homework, if you haven't already done that, the generalization to what's called two-mode squeezing. Okay, we'll talk more about that as time goes on. At the moment, I'm focusing here on squeezing of a single mode of the electromagnetic field. And it's parameterized, as we've done here, by this complex parameter in this particular way that I like to write it. It has a magnitude r, and I've written its argument as 2 theta. Okay? And the reason for doing so is that that operator squeezes the vacuum fluctuations along the quadrature theta, which is half the phase of zeta. Okay? So algebraically, this squeezing operator performs a unitary transformation on the annihilation operator, which is a Bogoliubov transformation, and similarly on the creation operator. And as we said, this, when applied to the vacuum, we get what we call squeezed vacuum, which has reduced fluctuations relative to the vacuum noise by this amount, exponential in this parameter, r. Okay? And if we were to look at the fluctuations along any other quadrature, we have this phase-dependent noise. And as I have emphasized before, squeezing is an interference phenomenon, if you want to think about it. It involves interference between different Fock states. And that interference is what allows us to see a non-classical effect whereby the noise is less than the vacuum level. Okay. And for example, we can see that if I haven't written this down before, but I'll write it down now. We can always express any state in the basis of the Fock states, right? The eigenstates of the simple harmonic oscillator. And this is the expression. Question, how the heck would you derive that?
Similar to that for the two-mode case?
You have to speak up, be a little more assertive in your...
Yeah, you can expand the exhaust like that and add to the...
Yeah, we have to think about how we would deal with this exponential right? I mean, this guy, as we just said, is right? And somehow we have to if we could separate out this exponential in some way, then we're golden. That's called a disentangling theorem. It's a general property of what we call Lie groups, of how we think about this as this set of unitary operators as part of a group. The group is actually known as SU11. But that's just because if you want to be fancy, you can say that. But you know, we've seen examples of disentangling theorems. For example, when we saw the example of the coherent states, and we wanted to express the coherent state as a superposition of Fock states. One way we did that is we said, oh yes, this thing can be disentangled using Baker-Campbell-Hausdorff. One of these guys is a star. Acting on the vacuum. So we've disentangled. That's nothing to do with entanglement in quantum mechanics. It's just an English word that's used in this context. The exponents, and in doing so, we can. This thing is the identity, right? And then this became a power series, and we got the Fock state. So we'd have to do something similar here, and it's not straightforward to do that. That's a complicated thing to do in general. But in certain cases, for certain groups, it can be done. And when you do that, in this case, you get this form. Now, important points to emphasize here is that, as we've discussed, and it's obvious, this state involves only the squeezed vacuum state involves only the even parity states, right? Thought about from the point of view of the wave functions, they're the wave functions that are symmetric under parity reflection along that. That's clear from the fact that this involves creation and annihilations of pairs of photons, which means raising by 2 or lowering by 2 on the Fock ladder. So that's how that comes about. And as you're studying in your homework, if you haven't already done so, and as we discussed last lecture, one of the ways we can think about where squeezing comes from, and we're going to start seeing this now in the optical context, where we would get, if we thought about this as a particle in a well, as a mechanical oscillator, one way we would drive a squeezed state is through parametric resonance. So if we were to change the spring constant of this well and change that spring constant periodically with a frequency that's equal to twice the resonance frequency, we would drive parametric resonance. And this thing would become a breathing wave packet, and the amount at which it got to at its minimum would be getting narrower and narrower and narrower, and wider and wider and wider. And we've all done this. We've all done parametric resonance, I assume, because we've all swung on a swing. And when you're swinging on a swing, you are pumping your legs up and down at twice the frequency. And if you do it at just the right phase, you will amplify and keep swinging higher and higher. If you start swinging in the wrong direction, you can de-amplify, right? So the way in which you actually amplify or de-amplify your motion depends on the relative phase. So it's a phase-dependent amplification. It's phase-dependent. It's a phase-dependent amplifier. That's actually kind of important. All right? Very good. All right. So the other thing we were talking about last time we met was the idea of Homodyne detection. So in a Homodyne detector, the main point is that we don't directly measure the signal, but instead we interfere it or we beat it with a local oscillator. Okay? So the idea is to have some signal coming in that before I measure this on, say, a square law detector, I would put on what we call a local oscillator. This is totally old-fashioned jargon, but it lives with us today. These are terms that came from radio engineering and God knows when, 30s, 40s, I don't know. It's weird. It's going to be the 30s again soon. I can't just talk about the 30s. So, the 1930s. I'm a 20th century guy. Anyway, the point here is that you get an interference between the local oscillator and the signal, and you put that on a detector. And what you would see on this detector is something that the intensity on the detector would be the intensity of the signal plus the intensity of the local oscillator plus some interference term. And that interference term depends on the phase of the local oscillator. So this local oscillator is assumed to be a coherent state. Which has some phase. Okay? And that interference term, thus, because it's interference, depends on the phase of the local oscillator. And through that interference term, we will get something that is proportional to the quadrature of the signal along the phase of the local oscillator, or depending, it might be shifted depending on the phase shift that is also induced by the beam splitter. If the beam splitter gives you a phase, then you would shift the phase of the local oscillator, but let's just ignore that fact for the moment. Conceptually, this is the important point. Okay? And so the important point of a Homodyne detector is that it is a way of measuring quadratures, or CV variables, continuous variables. So as opposed to where we think about photon counting, where we just see click, 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 click in a kind of Geiger mode, this thing is more of some signal that we think about not more as a continuous signal with their fluctuations upon it. Now, as we have described last time, this is what's known as a normal or standard or something or other Homodyne detector. And what we're typically interested in, particularly in the case of squeezing in the quantum domain, is the quantum noise or quantum fluctuations in the signal. And we want the noise that we see on our detector. I mean, our detector is going to have electronic noise, and that's going to suck, and that's going to ruin everything, but whatever. We're in theory land here, so let's just enjoy it while we can. But so putting that aside, we want to ensure that the fluctuations that we are seeing are dominated by these fluctuations. That's the thing we really want to measure and detect. And if our local oscillator is noisy, if we didn't stabilize our laser very well or something like that, then that would corrupt the fluctuation we would see, and that would be unfortunate. So one way to deal with that is to think about a balanced Homodyne detector where we subtract out the common mode noise of the local oscillator, and in that case we get rid of all of this stuff, and all we see is the interference term. Okay, that's known as a balanced Homodyne detector. Okay, and what we would then see is, in that case, whatever we would see is the quadrature of that signal at the phase of the local oscillator, right? Maybe plus I or something, plus pi over 2, depending on the phase shift. That would depend on reflection. And if the noise in the signal is a phase-dependent thing, it's different noisy at different phases of oscillation, then by varying the phase of the local oscillator and measuring the noise power on our balanced Homodyne detector as a function of the phase of the local oscillator, we'll see the characteristic behavior that is here. We'll see this kind of effect whereby we would see on this, as a function of the phase of the local oscillator, there is some level that would be the level we would see in the absence of the vacuum. So we could block the signal port, for example, and then to see what's the noise as a function of local oscillator. It shouldn't vary. And we'll see some constant noise level. But then, as we vary this, what we'll see is, something that might, look like where this is either the plus R and this is either the minus R. And at these particular phases, we would see noise below the vacuum level. And noise above the vacuum level. And that would be our signature of seeing squeezing. Okay? Right. So I want to say maybe a few more words about thinking about this from the point of view of the quantum theory. Okay? So let's just say, let's remind us a little bit more about the business about shot noise. Okay? So if I send some kind of coherent state onto a square law detector, right, the mean number of photons is the intensity or the magnitude squared, and the fluctuations, if it's Poisson, if it's a coherent state, is the square root of the mean, right, in that case. Now, if this is, let's just imagine that this intensity is very small. The mean number of photons is very small. And that mean number of photons, of course, is with respect to some temporal mode, right? Because how else are we going to mean when we mean by the number of photons? We mean within some time interval. then, you know, most of the time we see nothing, and then, you know, sometimes we see one, sometimes we'll see two, but mostly we see nothing, and we'll see some clicks like this, right? Click, 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 right? And these fluctuations of Poisson process is what we call shot noise. And as we've discussed, in the semi-classical theory, we really don't even have to think about the quantum state of light at all. We can just think about these random events in terms of the random photoionization effect that would happen in quantum mechanics, treating the field completely classically. But we've said that story many times to just remind you of that. We're looking at if we look in a different regime, if we look in the regime where, let's say, the mean number of photons is very big compared to 1, okay, what would we see in this case on the spiral chart? Well, if I think about the probability of seeing n photons, of course, that, if it's a Poisson distribution, right? But in this limit, we know that this thing approaches a Gaussian, right? As we've studied before. So that, what is that Gaussian going to look like? Well, it's going to have some mean and then some fluctuations, right? And those fluctuations are delta n squared, which in this case is n over something like that. Actually, exactly that. Right? And so what I would see on the detector in that case, instead of these discrete, I would see, you know, on the photocurrent would be, you know, would have some mean, and then there would be single value, it does goes big, but anyway, I'd see noise on top of the mean, right? With a fluctuation here of this equal to the mean n. So we would call this Gaussian noise, and because it's uncorrelated from any time bin to time bin, we would call this Gaussian white noise, which is the shot noise. And the idea, of course, is if I have squeezing, I can reduce that shot noise. Right? So if I were to take this local oscillator and inject into it squeezed vacuum into this port, what that would do is it would reduce the noise that I would see. I would see, if it's on, if it was at the right phase. Okay. Now you're studying this in your homework a little bit in the very famous now and incredibly relevant work of our own Professor Carl Caves, who in his PhD work back in the 20th century, sometime at the end of the 1970s, showed how one can improve the sensitivity of an optical interferometer by injecting squeezed vacuum into the unused port of an interferometer as a way of improving the sensitivity of the interferometer. In his case, he was a student of the Nobel laureate, now Nobel laureate Kip Thorne, to detect gravity waves. And indeed, their backs up or against the wall finally, 35, whatever, 40 years later. And they really can't improve the sensitivity of their interferometers anymore beyond the possibility of injecting squeeze vacuum into their interferometers, and it's now being used in advanced LIGO to try to improve the sensitivity for gravity wave detections. This is a major triumph of quantum optics, and we have a proud history here at UNM in relation to that. So that's a really important problem, and I urge you to really study that homework problem and think about it hard. Right. All right, there's more things I can say, and they're in the notes, but I think I want to continue on and say some other things. So, where the hell does squeeze light come from? That's a question you might have asked your parents when you were embarrassed and they kind of blushed about it. Where does squeeze things come from? Well, I'm here to tell you. So, what we've discussed in the past is if I have what we call a classical current, so if I thought in a very formal way, I said, oh, you know, in QED, the interaction between charges and the electromagnetic field is related to the interaction of the current and the vector potential, say, right? And you have -1/c, we get an integral over all space, right? But if we treated the current somehow, some way, as a classical field, ignoring its quantum fluctuations, then that interaction led us to basically the displacement operator. Coherent states. So as we've discussed now many times in the past, classical currents are the sources in quantized electromagnetic description of coherent states. And if the current itself is a stochastic classical variable, then the fields described within quantum mechanics we would say are mixed states, which are statistical mixtures of coherent states. And that's what we call classical light. And so such a source is not going to produce a squeeze state, right? Because squeezing anything which is a statistical mixture of coherent states cannot have fluctuations in any quadrature below the vacuum level. It will always have at least the vacuum level noise, if not more. Okay? So if the state is a, I might have a multimode coherent state, if it's a statistical mixture of coherent states, where this, as we've discussed, and we'll get into this more soon, this is the so-called Glauber-Sudarshan P representation. If that is an honest-to-God probability distribution, then this is classical light from this definition. And thus, such a state of the electromagnetic field must have, as we've described before, no matter what the quadrature is, it's always going to be at least as noisy as vacuum and never below. So squeezing ain't going to come this way. Okay. Now, one way we often like to try to create different kinds of light is by trying to use intense laser fields to generate other kinds of light. One approach to making other kinds of light, I will say, is through scattering. So I might think about the following situation where I have some kind of pump field, which might be classical in this description. Could be an intense laser beam. And I'm going to throw it at something, stuff, and have other light come out. That's what I mean by scattering. Okay. That stuff could be a crystal. It could be some beam splitters and phase shifters, whatever it is, right? So I have some input and some output. I could have lots of different inputs. It doesn't have to be one direction. And then I have output. And in that sense, I'm thinking about this kind of process as a kind of scattering process, whereby light comes in and light goes out. Okay? And the question is, what kind of scattering processes can produce non-classical light? Okay. So one way to think about this, if I think about, let's think about this from a kind of classical electromagnetic perspective to begin. Okay. So let's just think about this. So I'm going to think about this as I have some induced current that radiates. Okay. Now, when thinking about this, it's natural, especially if I'm thinking about this stuff as being dielectric in nature, is to think about it, that induced current, in terms of the dipole density, electric dipole density, or what is the polarization in Maxwell's equations, P, right? It's the amount of dipole per unit volume. That is the thing that radiates, right? The current is the derivative of the dipole. It's the dipole oscillation. Now, if I think about this in a kind of perturbative regime, whereby the induced dipoles that I get are related to different powers in the strength of the field, then we typically would write this in the following way. Well, and I'm going to write this in a little bit of a hand-wavy way to start. There might be an induced dipole moment proportional to the electric field, and that we would say is the susceptibility. Okay? So this is the how susceptible is the material to being polarized. Okay, call it chi1 here because it depends only on the first power of that. But I might have, and I'll write this in some loosey-goosey way, a chi2, which depends on something about two powers of the electric field. Now, what the hell am I writing E next to one another? I'm just saying whatever this is, it's really a tensor. You know, it's got two indices. So this has, you know, this is a piece of I would be I, J, K, I, and this would be J and K, and have to sum them over. But, you know, we can deal with that. Or maybe there's something that depends on the third power, etc., etc. And this kind of perturbative expansion is applicable if the binding energy of the electrons inside the material are tight, strong binding compared to the electric field strength that is pulling the electrons away. And we would think about this in a perturbative way. Okay. So, what we're going to be talking about is this kind of term we're familiar with, and we talked about this, we reviewed this elementary description last semester when we talked about the Lorentz oscillator. This is, of course, what we call linear optics. So the standard optics that we're typically familiar with involving lenses and beam splitters and what have you is linear optics. Okay? We typically just think about the index of refraction in a way that is independent of the strength of the field. That makes it linear. Okay? But these terms are all nonlinear. Hence, this is nonlinear optics. And there is an intimate relationship between nonlinear optics and quantum optics. Because as we will see in a moment, it is through nonlinear optics that we are able to create non-classical light. Linear optics ain't going to do it for us. Let's see why. So, if we go back now here and think about our interaction Hamiltonian in this making, as we have talked about in the past, the multipole expansion to take that current and look at the lowest order multipole, which would be the electric dipole, then, you know, this is real in the lowest order would be the integral of the P dot E. Okay, instead of J dot A, we have a P dot E type interaction, like a dipole interaction, minus E dot E, right, that we're familiar with. But now a density of such things, okay? So if we're thinking about this from the point of view of the quantized field now, okay, where now I'm going to talk about linear optics. Okay, before I do that, I'm going to say this. So my scattering operator, or the S matrix, if you've ever studied that, which would take input to output, would it be related to some time evolution operator that takes you all the way from minus infinity to plus infinity in the interaction picture, and that would be e to the minus I minus infinity h int, a function of time, dt. This would be the interaction Hamiltonian in the interaction picture, which is a free field. Okay, And what we see in this, in a scattering process like this, if there's nothing in the material which can absorb, or there's no gain in the system, then whatever energy goes in has to go out. And that's kind of would be enforced by this integral over all times. We would end up with delta functions with respect to the time integrals that would ensure that whatever energy went in, went out. And so that's would be kind of equivalent to the rotating wave approximation, and it's going to be something like, you know, it's only going to be things that are related to the conjugates, the things that have the creation operators have to be paired with things associated with the annihilation operators, because only those terms will be energy conserving. Is that clear? I'm waving my hands a little bit here, but the details are not so important. The physics is what's important here. So, in this kind of picture, for the example of the linear optics, where this kind of thing is something like chi1 E, in this case, E minus. What I'm going to see is that this scattering operator is going to be something that's going to look basically of the form e to the minus I sum over modes with some coefficients that I'll call lambda ij. In other words, what this scattering operator does is it annihilates a photon in some mode and then just puts it in another mode. That's all this thing can do. Like a lens, right? It would bend, it would take light, if it started in some ray, it would put it into another ray, or a beam splitter. Now it might keep it in the same mode, I could equal J, and then it could give it a phase shift. But basically that's all linear optics can do. It can cause me to get a phase shift in the mode, or it could take a photon in one mode and put it into another mode. That's all a linear optical element can do. Okay. Now, we studied this, kind of, in one of our last homework problems last semester, where we looked at this kind of thing in terms of thinking about this kind of problem of scattering for linear optics, where I had a certain set of input modes and then the output modes. And if I look at that scattering transformation, what is the output mode related to the input mode? As a unitary transformation. So this is whatever that scattering transformation is. If I have linear optics, which means my S matrix operator has that form, then this is just itself a linear transformation. In other words, the input modes are a linear transformation. I mean, the output modes are a linear transformation on the input modes. Where this matrix is just the matrix exponentiation of lambda. So if you think about lambda as a matrix, you exponentiate it, you get this capital lambda, which itself is a unitary matrix if it's lossless. No gain, no loss, no harm, no foul. Okay? So we've seen this. I'm just restating things we've seen before. For example, if I had, a beam splitter transformation, right? I have A1 in, A2 in, A1 out, A2 out. This is a linear optical transformation, right? Where I would say that I can write this, if I wanted, in some bastardized notation of putting operators in a column vector. So this matrix is just a classical transformation on the electric field amplitudes, right? It would say what this is, but it's not the same transformation on the operators, the modes A, as we would classically in Hecht and Sajak, or whatever your favorite linear optics textbook, of what a beam splitter, and this is my matrix lambda, capital lambda, which itself is a unitary matrix. Okay? All right? So, we have to, review that problem for homework. Now, if I, let's go back over here. If I input into this linear optical network, could be a bunch of beam splitters, phase shifters, optical fibers, routing around, making something, right? And I put in here, let's say, some kind of laser field with some, I'll think about it as a coherent state, a multi-mode coherent state. The question is, what is the state that I see coming out? Okay. So my side in, let's say, is a coherent state. Meaning it's some laser field treated, in this case, completely noiselessly. We couldn't make it noisy. What? Something to make it worse. Okay. So this is some displacement operator acting on the vacuum, which I could write sum over all the modes Everyone agree? That's the multimode coherent state in. So now my output state, the state that's asymptotically far away, that's scattered from the system, which is to say the photons go into the interferometer and then go out, or whatever it is. I apply the S matrix onto that. Right? Which is going to be equal to, and I'll play some tricks of the trade as we've discussed before, and plug all those guys in. We good with that? What did I do? Well, I played some tricks. What I did is I put a U here, but then I put a U dagger U here. The U acting on the vacuum does nothing. Why is that? Why is the U on the vacuum doing nothing? Well, if I look at how that unitary operator, wherever the heck it is, it's over there, this acts on the vacuum, does nothing, leaves the vacuum alone, right? Because it's got this annihilation operator here. It just takes things out of the mode and put them together, but there was nothing to begin with. You can't do anything to it. So that's fine. So I can get rid of that. And then I put these guys inside here. All right? Tricks. Tricks, tricks, tricks. Now what? Well, we got U and U dagger kind of in the other order. Let's come back over here. We got a U dagger U, and this got a U and a U dagger. I don't know, that's okay. Because I can, while this is true, what is also true is the time reversed is true, and then this has to be just that. Because that's just going backwards in time. Okay. All right. So now I can replace this with so then I got to take the dagger of that. Ooh, okay, before I do that. So now the question, if I take the dagger of this, let's take the dagger. That takes off the dagger here. All right, good. So this guy is equal to sum over J. I'm going to put the sum outside. Lambda ij a j in dagger. And this guy is written up there. Alpha ij dagger a j in. All right, That's nice. Now, let us collect terms. And then do the sum over I first. And this is just classically, so I'm going to put the star outside. This is alpha I out. In other words, this is the transformation by this same matrix, oh, an alpha j summed over I. This is, instead of thinking about the modes as quantum operators, I thought about those modes as classical fields, and this is the same transformation with the star. Did I somehow get it? This should have been an out, huh? Not an in. These are outs. And similarly, summing over I, this is alpha I out. Or j. Summed over I, this is j. So, with all of that math rigmarole, the bottom line is this. Let us summarize what all of this math means. What this means is that if I come back to looking at this picture, if I send in a coherent state, I get out a coherent state. Linear optics does nothing to the quantum fluctuations. It just does exactly the same thing as the classical dynamics would do. Now, one way to think about this is the following. Let's just emphasize the following fact. Because this unitary transformation is just a single photon by single photon effect, really what's happening is each photon is doing its own thing independently. A single photon goes into this interferometer and gets scattered with a certain probability amplitude. But every photon is doing its own thing in this kind of thing. And because the magic is because we have this kind of Poisson statistic distribution, the statistics, we don't have a single photon, we have some collection of photons, but the statistics of the photons are not affected when we had Poisson or super Poisson applied. These statistics are exactly the same as these statistics. So, the bottom line of all this calculation is that linear optics takes classical light to classical light. There's nothing you can do through linear optics to get non-classical current. Now, I just bring up a little aside here, which is one of the things that's been more shocking in recent years in post-21st century physics, which is linear optics can have surprising power if your input itself is non-classical. Suppose instead of sending coherent states into your linear optical network, you sent in single photon states. It turns out that's actually amazing what you can get in that situation. In fact, you can get statistics of your output of your linear optical network that are inconceivable from the point of view of classical statistics. Okay? And it was something that we were blindsided with, and I'm saying we, the collective quantum optics community, because we knew this was true. Linear optics seemed to be a boring thing because we know that it can't make things non-classical. But if you start with non-classical light, it's a different story. We may see that for homework. All right, so now we want to go beyond. We want to now, let's come back up here. Our question is to start thinking about nonlinear optics. Okay? So, we're going to spend some time talking about classical nonlinear optics. Very, very, very cursorily, we'll just sort of scratch the surface of it, but enough to get some of the essential physics that we're going to need to think about how we make non-classical light. Okay? So let's think about non-classical. So what can happen in this? Let's think about what we call chi2, this process. Let's just think about this one. Okay. So what can happen in this case? Well, let's look at the Fourier transform of our, so let's look at the polarization that is oscillating at some frequency omega, some particular frequency omega. How can that, where would that come from? Well, if we have, and so I also have my electric field. My electric field, look at the Fourier transform of that, some frequency omega, some particular frequency omega. If we had a chi1 process, a linear optics, then the polarization oscillates at the frequency of the electric field. That's linear optics. But in nonlinear optics, we can have different things. We can have a situation where, if I look at the polarization, say, it's a function of time, I might have a term that looks like the following. Well, I have my two fields, because I have E, two different powers of E. And I might have the following thing. I'm going to have E omega 1 chi2 at omega 3, which is equal to omega 1 plus omega 2. So there can be a term, a nonlinear optic term, whereby the fields that are oscillating, one at a frequency omega 1 and omega frequency 2, beat together through this susceptibility to create a dipole density that is oscillating at the sum of those two frequencies. That's something that can happen through a nonlinear optical process. This is called, shockingly, some frequency generation, right? So I can end up with a dipole density that is oscillating at the sum of the frequencies of the two fields. There can be another term in here that might be related to the following. The beat note might involve the difference, because I can have E plus E is equal to E plus E star. This term is another effect I can have, whereby if I take two laser beams, that one that's oscillating at frequency omega 1 and one that's oscillating at frequency omega 2, there is a beat note between them at the difference of those two frequencies. And if there is a susceptibility, a chi2 susceptibility that is strong at that difference, then the material will oscillate at this beat note in a way that depends, intermediated by something about the material that says something about that beat note. That's another potential term, a potential nonlinear optical process. This is some frequency generation. And this is difference frequency generation. And this is, it's through this kind of processes that, you know, the optical engineers and physicists take a few of the artist's colors that lasers put out, mix them together to get other colors of lasers through sum and difference frequency generation. If we have a chi2 crystal, which has the right susceptibilities to generate those frequencies, okay? So let's talk a little bit about how we would describe this kind of nonlinear optical process through the point of view of Maxwell's equations, okay? And then we're going to turn our attention next week to the quantum description and how this allows us to create non-classical light and squeezing in particular. Okay. So, how would we describe this? Well, I can look at the wave equation. So here I am, here's my chi2 crystal. I got this field. Let's say, well, let me be fancy. I have my omega 1. That's some laser beam. I got some other laser beam going through here, frequency omega 2. And through this process, I generate a third beam coming out at frequency omega 3. Let's, in particular, as an example, let's just look at some frequency generation. Right? Now, I mentioned these don't have to be two different beams. It could be one beam and then I add omega 1 and omega 1 together and get 2 omega 1. That's called second harmonic generation. Everyone's favorite some frequency generation. All the optics guys are going to. But anyway, we'll move on. All right. So let's quickly write down the wave equation that would describe this. So I'm going to look in the Fourier domain. I'm going to look at a particular frequency, and let's say my wave equation here. And let's just think about this as propagation in 1D. Let's forget about this. Think about this as plane waves. So we'll forget about the transverse modes and all of that. Let's just think about it as propagating along the z direction. The wave equation, which is Helmholtz equation, for wave 3 oscillating at frequency 3. So this is the Helmholtz equation. Right? Del squared minus d by dt squared becomes this, where this is the wave number, k. K, of course, is equal to the index of refraction times omega over c. Is equal to what? Well, you know, that is equal to, in my favorite units, 4 pi over c squared d by dt of p squared, which is omega 3 squared, the polarization density at that frequency. Okay. Now there might be a 1 over epsilon naught if you're so inclined, but I'm not so inclined. All right. So let me just make sure I got one thing right. Oh yeah, that's right. Should have a minus sign. So that's just the wave equation with the source. You can go back and check it yourself. This p we just wrote down. This p is equal to minus 4 pi over c squared omega 3 squared chi 2 at omega 3 times the electric field at omega 1 times the electric field at omega 2. So this is a nonlinear differential equation. Oh, I guess I should be a little bit more careful here because this is all good so far.
Are we missing a complex complex conjugate?
Not here. This one is the sum frequency generation.
Mm-hmm.
If it was a different frequency generation, then it would be the conjugate
right.
term. Okay? And we're going to come back to that next time. Okay. So our goal will be to see how this kind of equation can give us either, depending in this case, some frequency generation, or it could be different frequency generation. What the classical field theory tells us, and then how we connect that to the quantum field theory. And the relationship of that will be different than this situation, whereby we just, here, all that we could do was redistribute photons amongst the modes. And that did nothing to change the photon statistics. Okay. However, when we have this kind of process of mixing of different modes, this will obviously involve, the process involve more than one photon. And it's the fact that nonlinear optics involves, in some sense, the interactions between the photons, and not the photon by photon transformation, is through the where the photon correlations occur and the non-classicality occurs. All right. So we'll pick that up next week.